Going to shut it down. Okay, let's start. Good afternoon, everybody, and good morning. Vincent, it must be morning for you. And welcome.
Yes, that's correct.
Yeah, welcome
Thank you so
everybody to.
much.
Can you hear me clearly? Is there a lag? No, okay. So, welcome to the second session for the Quantum Pulse. This is a series that we've started to make sure that people are aware of what's happening in the quantum space. And unlike earlier, we don't want to do anything about what is quantum, what are the basics. This is that all that has been done and dusted, not just by us, by so many people in the ecosystem. And most of the audience that we have is from the quantum ecosystem. Occasionally, there are a few people from the end user industry also who are joining us. And so, what we want to do is look at the topic in a little bit more depth, and that's the theme and the focus of the sessions that we've been having. Today, our discussion is going to be focused on computing architectures. When we look at quantum computing, there is a lot of different kinds of approaches that are being taken by companies across the world. And and there has been an evolution, a lot of progress uh, in different kinds of architectures or different technologies that people have adopted for computing. So what we want to do is go through the landscape a little bit, and to do that, we have some very eminent people who are, from the quantum industry and who are deeply involved in some of this. So we have Venkat Subramaniam, who's from IBM, and Vincent van Wingerden, who's from Classic, which is headquartered in Israel, and Sujoy Chakravarti, who's associated, he's the CEO for Confluence. So here we are looking at very different kind of representations in terms of the technology focus, where on the stack the companies are focusing on, and so on. Ideally, a panel like this should have included 10 people, but that's a kind of little difficult to get into the discussion. But the folks here are not just representing their own companies, but they also are very familiar about what's happening in the rest of the quantum world on the computing side. So we're going to leverage that experience. So thank you very much for taking the time, the three of you, to be here, and then for the for the benefit of the audience. I'm going to request all of you to introduce yourself, give a little bit of background, your quantum background, and then we'll move forward from there. So over to you, Venkat.
Yeah, thank you. Thank you so much for having me here. It's really a pleasure to join you and this distinguished panel. So I'm Venkat Subramaniam and I'm the IBM Quantum India lead. And over here, we are focused on, of course, research, product development, and also in the ecosystem building. So yeah, that's the short about me. Thank you so much.
Sujoy?
Yeah, hi, this is Sujoy, and we are a quantum computing startup out of India, and we do quantum hardware. Our focus is on the photonic quantum computer, which is a very different way of trying to build a quantum computer. And yeah, as we go ahead, we can discuss what we do, how we do it, and why we do it, which is probably the most important question. Uh, and our office is primarily based in Bangalore. That's where we are building out this computer. It's going to be a full stack machine when it gets built.
Thank you. Vincent, over to you.
Yeah, so welcome everybody. My name is Vincent. I work as said for Classic. We are a quantum software company. I've been working in the software quantum space for roughly 6 years now, mostly focusing on the software aspect and applications on how we can use the physical hardware when it is available.
Thank you. So, since I talked a little bit about different kind of computing architectures and technologies that people are working in, Venkat, could you, for example, share a little bit about IBM's focus on quantum, more from a technology stack perspective, and what is the approach that you're taking, and why superconducting qubits, and what does the long term look like? So take your time. I'm hoping that all three of you take 4 to 5 minutes to talk about this in detail. Yeah.
Yeah, sure. So yes, so as you rightly mentioned, IBM's approach is the superconducting qubits. And we are not only working on the hardware aspects, but the full stack, which means, the qubit technology, the components, then the middleware, and then finally the software and applications on top of it, right? So for any quantum computing application, what are the main ingredients, or what do you have to do, right? So number one, you are looking at the scale, which is the number of qubits, right? Okay, how many qubits can you achieve um, for your computational needs, right? The second is the quality of these qubits. So in terms of error rates, single gates and 2 qubit gates, what are the error rates that you are achieving? So that's the other important aspect. Then the third important aspect is the speed. Okay, so in terms of, so if you are running some circuits, how many circuit operations are you able to complete in a second, for example, right? So these are the main considerations. So scale, quality, and speed, and that determines performance. So today, if you look at the performance, superconducting qubits give you the best performance on these three metrics, right? So on scale, quality, speed, all of these, uh, you see that superconducting is the one which is able to give you the number of gates you require, the number of qubits, the error quality, all of these, right? So that is one of the key reasons why we in IBM believe in superconducting qubits, and our focus is entirely on this, right? So the qubit technology is that. On top of that, the middleware and the software, that layer is driven by Qiskit. And Qiskit, as you might be aware, is a Python library. So the entry barrier is very low. Anybody who knows Python can start coding on it. And there again, the goal is to make it the best, right, in terms of various benchmarks. And, late last year, we demonstrated that on various benchmarks, Qiskit performs the best. And also it shows in terms of the adoption itself, right? So you have about 70% of the quantum programming today done in Qiskit. And in fact, even other non-superconducting platforms are also sort of going with Qiskit and adopting it. So I think when you talk about quantum computing, the goal is how do you make it usable? And usable, you need to do well on some of these benchmarks. And I think that has been the focus of IBM so far. Yeah.
Thank you. And you sort of explained why superconducting qubits, because that's the progress that has been made. IBM decided to focus on superconducting qubits. And then, of course, there has been progress, and IBM has shared a roadmap going forward. So when do you think, uh, how much confidence do you have on that? Does IBM have on that roadmap? Are you meeting all the roadmap projections made earlier? Where do you
Yeah,
stand?
yeah. So since 2019, when it was first published, right? So we've met each of the targets that have been set for it, right?
Mhm.
So in that sense, yes, we are all meeting all the targets, and if you look at it carefully, I think the error-corrected qubits start showing up in 2029. So that roadmap, I mean, this is a very confident roadmap that IBM has put out, and so far it has always been met, and there is no doubt that we are going to meet it going forward too.
Sure, thank you. So,
Thank you.
Sujoy, maybe you can talk about now, since we've discussed superconducting qubits, maybe you can throw some light on photonics-based computing, and uh, maybe explain about the area and then the approach that your company is taking as well.
Yeah, sure. So Venkat, as always, has done a superb job of explaining what is important in a computer. And uh, the three things he mentioned are the most important things, right? But as he said, right, if you look at the roadmaps of IBM and Google, the roadmap says that we will have quantum computing, but it does not really accelerate fast enough, right? And the world wouldn't have been looking at other technologies if we were 100% sure that superconducting is the way to go, that we will get usable machines which can be used by the software guys to run real software programs. So what people figured is that is not happening because of a few essential problems that exist with superconducting, and not just superconducting, with any form of qubits. Right? The first is the coherence time, the stability of the qubit itself, and the fact that almost all quantum machines require you to cool something down, right? And that is a fairly complicated thing to do. So can we avoid cooling is a question which everyone grapples with, right? Can we stay coherent for longer without requiring a very high level of cooling? The other one is scaling. When you scale a quantum computer, can every qubit talk to every other qubit, which would make it a beautiful computer, because the algorithm might need you to talk to a qubit which is far apart in space or time. So how do you do that? So with these questions in mind, people started exploring other alternatives. And as you know, there are probably 15 different ways quantum computers are being built. And one of the earliest quantum computing approaches, right, or the way people understood quantum computing, the early experiments, was photons. It never took off, but life has come a full circle, and there are people now who believe in photonic quantum computing. So what's happening in the space? Right? So there are two ways of looking at photonic quantum computing. One is what you call a single photon. Right? So you have a single photon, and the quantum state of that single photon is either its spin or its presence or absence, etc. So these are the two quantum states. You do the superposition, etc. You run everything based on that. And this is the approach that a very well-known company known as Psi Quantum is taking. Right? They are promising that they'll come out with a million qubit machine based on this technology. They're spending billions of dollars doing that. What we do and what a few other people do is a slightly different approach. It's called the continuous variable paradigm, the CV paradigm. So what we do here is that instead of using a single photon, and in order to avoid some of the issues with the single photon, you take a bunch of photons and manipulate their electric fields uh, in quantum ways. Right? So based on how you manipulate it, it's a quantum 1 or a 0. Then all the other stuff remains the same, right? The same mixing, etc., etc. There are few advantages to doing that. There are advantages on how these qubits interact with each other, how probabilistic versus deterministic they are, etc., etc. And the manipulation of these qubits has been shown that as you measure out these qubits, you can actually manipulate the entangled qubit. So you can do quantum gates using this property. So that's the methodology that we use. It's called the continuous variable. So there are a few other companies who are also trying to go down the same path. What happens is that yeah, the technology here, the issue with the photonic technology, or where a lot of research or a lot of our time is going, is how do we reliably generate these quantum states and keep them keep its fidelity high. Right? So that's where the bulk of the research is, and that's where people are using different kinds of schemes to go figure out what is the best way of doing this. So I think a photonic based quantum computer is going to be a reality. There are people who have demonstrated 1 to 4 qubits, but with a larger number of qubits, getting a machine out there is going to be a reality. Maybe 3 to 5 years into the future, that's when I expect to start seeing more of these photonic based machines coming out. And obviously, the best machines are the ones which will win, whichever technology they are. And there's also a feeling in the industry that various different machines might be good at solving different kinds of problems, and so people might use machine A to target one kind of problem, machine B to target another kind of problem, and all these machines might coexist. I can't
Rina,
hear you,
you're
Rina.
muted.
So yeah, thank you for pointing out that I'm muted. Thanks Sujoy for sharing that perspective. And to your last statement, I think we'll spend some time discussing that. After we have completed this round. So over to you, Vincent, to share your perspective, because I know your company is working on the software stack. So help us understand your the approach that your company is taking. But before that, if you can make a comment on the different kinds of hardware approaches in terms of what you're seeing and what would you like to tell the audience about that? Yeah.
So for me, talking about hardware is not easy because I'm in the software space. But I mean, what I'm really interested about at the moment, and I think that we are seeing becoming more and more real, is error correction. Of course, at the moment, it is more keeping states alive longer than both doing error correction and really going towards a full logical error-free qubit. But this is still an area of research that I find very fascinating because it will be needed to execute the actual programs that we want to do, and to give the value probably that we want out of quantum computers. So for a hardware state, it's hard for me to say anything about any modality specifically, but I'm very excited about the progress that has been made in the fidelity of the qubits in each platform, as well as the error correction on top of that.
Okay, sure. And a little bit about the work that your company is doing, Classic.
Sure. So what we do is when quantum computers started, most of the programming was on a gate level. So it could be comparable to writing assembly code or machine code when we were writing that for when computers just started. The idea of Classic is when you want to write very large scale quantum programs that will allow you to, for example, solve Shor's algorithm, or if you want to do specific molecular simulations, then writing at such a low level is impractical, for one, and two, it will also could not always give the ideal circuits or the ideal programs that you want to run on these quantum computers. So the idea of Classic is to start working at a higher level of abstraction. That means that programmers for quantum computers will have a programming language or a programming infrastructure that is closer, for example, that we have today in the classical world to C, to programming languages like Python or other modern languages, and that a user do not have to think about the gate-based implementation on a quantum computer. To program at a high level of abstraction And our compiler technology will then generate a gate-based circuit that can be executed on any quantum computer that can take gate-based instructions, whether that is superconducting, ions, photons, whatever. The unique thing here is that when we compile our program from our high-level abstraction to the gate level that is interpreted by the actual computer, is that you can computer to our compiler. So in these two cases of the other panelists, it could be that you say, well, I have a big Grover algorithm that wants to solve a specific arithmetic expression, and I'm going to give the specifics of an IBM computer, which is a heavy hex architecture with specific native gates. That would create a circuit that is optimal for that specific hardware. So it is optimal to run on IBM. That is not transpilation. We are a level above that. So we will generate a logical circuit specifically for the architecture of IBM. Now let's say we want to do that on the computer of Sujoy. Then we do not change the code. You just say, well, this is the architecture of that machine. Maybe it is an all-no connected machine. It has probably different types of native gates. Then our compiler will take the same high-level language. It will compile it down to a gate-based circuit that is optimal for that specific machine. So basically, we allow programmers to not worry about gate-level implementation. They can worry about functional programming, just like that's been done in classical machines. And we worry about an optimal implementation for any type of hardware, either now or a future architecture. That is what we do.
Okay, thank you. I think coming back to the technology architecture, Venkat, if I may ask you that if you look at IBM's approach, and of course, we look at other there are other companies also who are working on superconducting qubits. Do you think that there are other technologies that may have breakthroughs? There are around, as Sujoy pointed out, there are around 10 to 15 other technologies that people are approaching. Some of them are very less, maybe using it for different purposes. Like, for example, NV diamond centers based technology was initially considered for computing, but is now widely being used for sensing, right? And still, there are people who have not given up on the computing side, although some of them have. So, what do you think about as you look forward into the future? Do you see multiple of these technologies winning out, complementing, supplementing? What do you think is going to happen from a technology stack perspective?
Yeah. So I right now, okay, my belief is in terms of the single processors themselves, probably superconducting is going to win. Okay, it's my. So you are talking to a believer of quantum, superconducting technology, right? So that's what I believe in, right? But you're right. There are possibilities where you might see some hybrid approaches emerging in future, because right now you're seeing the emergence of what we call the the quantum supercomputing era, where it's not a single chip which is doing all the qubits are not sitting on a single chip. If you look at the IBM roadmap also, we are saying multiple chips interconnected, and that's how you are increasing the number of qubits. And also, like it was mentioned, you're also, like Vincent mentioned, there is error correction sitting on top of that. So yes, there is a little bit of engineering where you might see other technologies also come in. But my belief right now, if you ask me, it is superconducting all the way. Okay. Now, there are also people do raise this question that, oh, that needs to be cooled. Other technologies don't need to be cooled. But if you look at it, most of us have CPUs sitting on our laptops, right? Um, when we want to run AI programs, we go to the cloud to access GPUs. That's how the world is working today. So in future, what we are going to see is a combination of CPU, QPU, and GPU. And maybe the QPU, like you said, could be multiple types of QPUs sitting out there. Some of them for specific tasks, maybe they are much, much better. Or between interconnecting chips, you are seeing other kinds of technologies come in. Maybe some of it goes into quantum memory. So there are a lot of moving parts here, lot of innovation that is happening, lot of people working on it. But I don't think temperature should be the criteria right now, because in any case, CPUs are powerful, they do what they do. For specialized processing, we go to GPU, we go to QPU, which are sitting somewhere. It doesn't matter where they are, whether they are in a fridge or under the sea or where they are, it hardly matters to us, right? So at least that's how I see the technology evolving, where we have, each of these has their own strengths. So I keep telling, something as simple as multiplication, you need to do it on a CPU because it's much slower on a QPU, right? On a quantum processor, you can't be doing multiplication there. So multiplication you have to do on a CPU. For your AI tasks, some of those matrix operations and all, you have to go to GPU. And then the QPU has its own strengths. There are certain problems we know, for example, nature simulation, optimization. For these, we know it is good. So for that, it's going to go there. Now, of course, there are people who also show that annealers are good for optimization. That's one small class of problems, right? So, I mean, I see all these technologies in future becoming much, much cheaper, and also all of them being available on the cloud. You just access what you want. That orchestration is going to be key, because the user shouldn't be sitting and saying, oh, this one goes there, this one goes here. No, that's not going to work. So that orchestration of the job for the user has to be very simple, and that's what something like Qiskit is trying to do, right? As a user, and that's what Vincent also mentioned. You don't want to be specialized programmers to write your programs. This is the era of AI writing code for you, right? So you just want a simple interface, say this is what I want to do. The job orchestration is the middleware's job, says this goes to this QPU, this goes to this CPU, this one goes to some GPU, whatever. I think that's the future. Yeah.
Thanks, Venkat. I think you have uh, in detail spoken about the aspect of how how the CPU is going to work out, right? And a little bit of how, in combination, if you look at the QPU or the quantum processing unit, so you focused on that and how that is going to work along with the CPU and the GPU, and how they are going to complement each other. And through the example of this arithmetic operation, you don't want to use a probabilistic machine for a definitive answer, right? So obviously you want to continue to use all of those, and in the near future, we are going to see a hybrid usage of all of these. And fair enough, I think that's a very, very powerful point to make. I'm going to switch the conversation a little bit when I discuss with you, Sujoy, because I think that is one angle. Now, as Venkat was speaking, I was thinking about how today, when we look at computing, there is this large machines, the cloud, but then there is also this edge networks. There is also this whole concept of where does computing sit? So computing sits in routers as well as gateways, and in sensing devices also these days. There's a lot of embedded stuff if you look at the landscape of computing today. So, and the reason I'm bringing this up is because photonics is not just about computing, but also photonics is the main focus from a communications perspective. So do you want to throw light on this complementary aspect of different technologies from a photonics point of view? And if you could, go beyond the scope of the large computing space and also throw some light into the computing that sits everywhere and talk a little bit about that. You're on mute.
Yeah. Can you just repeat that last sentence because I couldn't catch the last sentence. You're breaking up. The part before that was okay.
Yeah. So the last sentence was that
computing where?
It's a computing in the context of a machine like a quantum computer, but also in terms of if with an analogous to how we see computing sitting everywhere today in smaller devices on the network and so on. So using that, can you throw a little bit of insights into complementary technologies from a quantum
There's some
perspective?
problem. We are not able to hear you well.
Yeah, exactly.
Oh, you're not able to hear me?
So Rina, it's apparently not just me. Yeah, I think others cannot hear you as well.
Let me try switching off the video and see if it's a bandwidth issue. Are you able to hear me?
Yes, I can.
Okay, maybe a bandwidth issue. Okay. So let me repeat that question. I said when Venkat was speaking, he spoke very beautifully about the role of the QPU and the CPU and the GPU and how it fits in together from a larger perspective. I wanted to shift the discussion because when he was talking about that, I was thinking about how we look at computing, how computing is distributed today. So there is, apart from the cloud, there's computing on the edge, and then there are smaller devices which have computing in them. The network has computing elements embedded into it, right? So when you look at from an alternate technology like photonics perspective, since photonics is equally is a technology used for communications, can you talk a little bit about the complementary aspects of different technologies from a quantum perspective with a focus on computing, on photonics?
Yeah, sure. So I think Venkat made some very good points. I am I'm happy that he believes in superconducting, and for me, any kind of quantum computing, I'm happy because it moves the needle forward. But what is going to happen in this world is that we are going to have 10 types of computing, which are all specialized for a certain thing. And the software players are going to play a very important role here, right? Because the end user should not care what solved this problem. The end user is going to just get the best solution, right? And I think 10 is probably a low number. It's probably much more than 10, right? Because people are going to do FPGAs, ASICs. They are also computing in one form or the other. And a form of computing which has been talked about for a long time and has never taken off is probably the edge computing, where you will do autonomous decisions on the edge using certain forms of computing. Okay, can a quantum computing go sit in there? I think the answer to that question is probably yes, if you find a technology which can operate in the field. Right? Today, quantum is struggling to find that technology, but maybe photonics is that technology, right? Which is why in the communication space, etc., uh, people are talking about these quantum repeaters or the QKD systems, etc., which don't require any special uh, devices. So maybe photonic-based quantum computing can operate small computers on the edge, which may not be as powerful as one of IBM's computers, but which does that small little task which is required. I mean, let's call it a quantum ASIC, right? So I think that's what will happen in the world. Computing will get distributed over various things. One of the other things is the optimization problems today, right? The D-Wave machines solve optimization problems, which is a lot of the quantum computing problem solving today. And this can also be called quantum inspired because you're not using a gate-based quantum computer, but you're still, evaluating the whole problem space at one time and solving for it. So So one of our other products, for example, is that machine, which can behave like a D-Wave machine and give you solutions exactly like that machine does. So it's quantum inspired, not fully quantum. There's a element of photonics to it, but it's an important part of computing. You don't need to throw that problem at a full-fledged gate-based IBM quantum computer. You can throw it at this small box, which is ruggedized, which can be mounted on a truck or wherever, and keep getting these optimal solutions. So I think that's the future of computing, and the software guys will make this completely transparent to the end user. The end user will just be happy with the fact that he's getting a solution. I think that's my view of where this entire thing progresses.
Thanks for that. Can you hear me clearly? Okay.
Yes, we
So,
can.
Vincent, over to you. And I think the question that I have for you is, again, extrapolating on the software side, when you look at a software developer or somebody who's working on a solution, leveraging quantum computing and classical computing and AI, for example, how are software solutions going to look like in the future? And how is it going to be made very simple for people as we move forward, hiding all the complexities away from them? But looking at an integration of different kinds of technologies and for different scenarios. So,
Yeah, so looking at a programmer experience, I think that there will be, even in the future, very, very limitation on people who have a deep understanding of quantum physics. So that is why I truly believe that we need a programming language that has a higher abstraction level, which will lower the bar of entry to each specific to the field of quantum programming. That is our goal. That's what we want to achieve. And next to that is we need a technology similar to what we have at the moment in classical computing. If I write some Rust or some Python code, it can run on, well, unfortunately, there's not many different types of hardware in the classical world left besides AMD and Intel, which use the same instruction set, but we, of course, also have ARM, RISC things. You want to be able to write a high-level program and then run it basically everywhere, which is now achieved using compilers. And that's something that we should have in the future as well for quantum computers. And that is exactly what we are hoping to achieve, where a programmer can easily give its intent, write that in a high abstraction manner, and using a compiler will be able to execute it on a machine that is good for that specific task. And I think what Sujoy said in the beginning is something that we will know in the future whether it will hold true or not. But it's something I understand as well, is maybe there are certain problems that will fit better on one type of QPU and certain problems that will fit better on another. And if you have a high-level abstraction language, it's very easy to say, I have this problem. Please compile it for an ion trap-based machine, compile it for superconductors, compile it for photon, see the resource requirements. Also, very much keeping in mind the overhead of error correction. And then you can say, well, I'm going to pick this specific computer. That is where we should be going. And that is hopefully where both hardware as well as software will guide us to. I hope that answers your question.
sure. So now a different question. Apart from the technology that your company is focusing on, which other technology would you place as the second choice? Venkat. And Sujoy, whoever wants to answer first.
I mean, there's not there. From our perspective, there are other languages, for example, Q#, for example, CRISP, that do offer also the idea of a higher abstraction language, and that you do not have to go down into qubits that much, that really focus on a high level of abstraction. At the moment, as far as I'm aware, and I'm happy to be corrected, there is no other compiler technology like ours that actually translates a high-level program into a circuit based on the specifications of that specific machine. if there is, I'm most definitely happy to learn something new today.
Sure, thank you. Venkat, Sujoy, whoever wants to go first.
So I can, say, so there are very exciting results coming from photonics, and as Sujay mentioned, it's going to be crucial in quantum communications, right? So that's something which will totally depend on the photonic, qubits to do its thing. But we are also now seeing ion traps, neutral atoms, all of them showing some very promising kind of results. So I think it's an open field for anybody who wants to innovate today. Very exciting times and a lot of good challenges as scientists. But which one gets translated into technology? It's a tough question to answer, I feel.
Sure. What about you, Sujoy? What do you think?
Yeah, Venkat hasn't stuck his neck out. Neither do I want to do that. I'm actually excited about the semiconductor-based technologies because again, it's the technology readiness or the compaction that those guys can achieve is well known. It comes from a technology which is very very mature. Question is, can they build the qubits into that? I mean, if they can, I feel that is exciting. But who will win the race to build the first of these computers? I really think that Venkat will. So I think the first usable computers are probably going to be the ones coming out of IBM and Google.
Okay.
Can I say one thing about that?
Yeah, sure.
It is a party we also work with. I mean, we also work with IBM, so it's not like that's the only ones. But I'm very excited about the work from companies who focus a lot on very high quality qubits that will allow low correlation between physical and logical qubits. And so for some roadmaps, so for example, also superconducting, but taking a different approach, which is Alice and Bob, they can do very, very high quality qubits with just, and that makes me excited because then you only need a few handful of physical qubits to create a single logical qubit. And I think that is a very interesting approach. At the moment, they are very far from the scale that IBM has. But if you're able to make that ratio super small, then maybe you can scale up in the logical world pretty quickly.
Great. I think that's a great answer. And that reminds me that recently there was the announcement by Google about the how correlation about this exact correlation between logical and physical qubits. Anybody has any thoughts on that?
Sorry, can you repeat the question?
The recent announcement by Google about how they've achieved better error correction. So the ratio of logical to physical qubits and scaling up is better now.
Well, it's not per se better. They have shown that it works. That is very unique. This is one of the first experiments that have shown that if you increase the distance of your error correction, that the logical qubits become better. Maybe it's good to say one thing, and maybe the hardware guys should answer this instead of me. But at the moment in the literature, when they're talking about logical qubits, these are not qubits that are logical in the sense that they're perfect. They're just better than their underlying physical qubits. And what Google have shown is that if the distance of the error correction gets better, the logical qubits quality becomes better.
Mm-hmm.
So that is extremely interesting because that means basically that the theory of error correction works, which is needed to build a real large scale quantum computer that can do the things that we wanted to do. So very quickly, that was what I had to say about that. And maybe Rania, if there's time, there's also some questions in the chat about other specific modalities.
Right. So we have kept 30 minutes for that, so we can
Oh,
use
perfect.
this
Okay.
discussion. Yeah, yeah. So any thoughts from Venkat or Sujoy on that?
So error correction, as Vincent pointed out, it is you are showing it. There are different approaches, like IBM has its codes, LDPC. There are surface codes, various kinds of codes that people are using at this point. Have we reached that end point where we have achieved it? No, we haven't. So again, just like the different qubit technologies, there are methods which allow you to scale, right, to number of qubits. You might achieve 5 qubits with high fidelity using one method, but it might not scale. So the same goes for error correction also. You need a scalable code which enables you to uh, as Vincent also and you pointed out, to achieve with minimum number of physical qubits, so you are achieving that logical qubits, right? So there is a distance to go, and if you see the IBM roadmap, we are saying 2029 we are going to have 200 logical qubits by then. So I think, this is an exciting area again, and this is again a debate for multiple different ways of doing error correction also.
Any thoughts from you, Sujoy?
Yeah, I think we need to read that announcement a little more carefully. And basically, what that announcement says that, as you scale the number of qubits, in the past, the number of errors has gone up. But now we have a case where, you scaled and the number of errors has gone up, but not by that much. So it's the curves are diverging from each other, which is a good sign, but which does not mean that we have achieved a usable computer. So good signs, and I am looking forward to 2029 when we get that error corrected qubits coming from IBM. That would be the real fun stuff once we start getting error corrected qubits.
Yeah, I also feel that
Because
that needs.
the reality today, right, is that there are quantum simulators or emulators out there, right? You can take an NVIDIA GPU and build a pretty powerful quantum simulator which can do 29, 30 qubits, which are error corrected. And the software guys can actually write software on that and show something happening with 30 qubits. So I think the real hardware still has a way to go to catch up there. And this announcement just said that we have come to a point where the curves are starting to diverge from each other, which is good news.
It is good news. And I feel that from the end user perspective, all such information should also have information which shows the trade-off, right? So for example, while this is good news, it will be important to know what is the ratio of the physical to the logical qubits and how does that change as we are looking at these uh, scenarios, right? So because true scalability can only be measured unless and when you know all the parameters that are involved, right? So that's but it's interesting. Definitely, wherever we see a release like that, it shows that press release like that, it shows that we are making progress in the community as a whole, and that's great. Now, I have one question from all of you. What is your experience with end users? And what are you where are, how, if you're already interacting in India with end users, what is that looking like? How, because, the reason I'm asking this question is a lot of end user community people are also in a doubt. Are others working on it? So it's good to know what is happening in the rest of the world as well as what is happening in India. And so that question would be valid for Venkat and uh, Vincent both. I think Sujoy, given the state where your company is likely to be, being a startup in this space, recent startup in this space, maybe you can look at this question differently and think about how uh, where do you see the first usage coming in? Are you going to wait for the full-fledged quantum computer, from a photonics perspective, or are there other uses to the technology that you're working on? So with that, I'll open it up to all three of you, whoever wants to speak first on this. Venkat, please go ahead. Yeah.
Okay, sure. So, yes, so I think what we are observing is that from India, the usage is very, very high. Okay. So we have these open quantum systems, which is open for anybody in the world to come and use. And these are real quantum systems, 100 plus qubits that people can use. And we are seeing extremely high usage from India. The number of Qiskit learners from India is amazingly high. The number of Qiskit, people who are who obtain that certification is extremely high. Probably US, India, it's like that. Okay, so the usage is amazing. Okay, in terms of end user adoption, in terms of students, in terms of software engineers, that is probably up there in the world, number 1, 2, like that. Okay. Now, also, you mentioned in terms of what are they doing? So many of them are probably at this point learning. And also we are seeing, if you are doing machine learning, you then come and compare that with quantum machine learning. I run this classification task on a classical computer. I now use the free credits to come and run a quantum machine learning for that same classification task and try and compare. And that is what we are observing most end users today trying to do. Now, of course, 30 plus qubits are now there on simulators. But also with the utility paper last year, it was shown that, once you reach 100 plus, brute force simulation is not going to get you that. Okay. And so already, for example, IIT Madras, we had this paper on protein folding. Protein folding, as you know, AI in protein folding won Nobel Prize in chemistry last year. But that still, AI still doesn't solve everything, because wherever there is limited sequence similarity, AI fails there, right? And so quantum comes in. And those kind of results are very promising coming out of India. And you might have seen IBM Jay in the one of his keynotes end of last year mentioned that we expect a quantum advantage in the next 2 years. Okay. So at least our goal here is to get that quantum advantage out of India. And we are going to see, in my strong belief also, that quantum advantage will be achieved well before error correction is, full error correction. With just error mitigation, we should be able to achieve quantum advantage. And we saw it in classical also, 1950s, when Hamming discovered the error correcting codes. In computers, it came 1 or 2 years later, but computers were useful even before error correction. They were used in World War II and many other places. So even in quantum, I believe, that even before error correction, we will start seeing quantum advantage. 2029 is quantum advantage. 2027 is when we are saying 26, 27, that you might just see quantum advantage.
So Venkat, if I sum it up properly, I think you're seeing a huge talent base in India because a big number of people are using Qiskit. A large portion of them may be students and people who want to learn and who are wanting to shift from being programmers on the classical side to start doing solutioning on the computing side, quantum computing side, and also possibly compare performance and see where this is likely to be useful. So that also tells a little bit about the stage that many people are in. But what I heard you say is that at least with institutes, probably in partnership with companies, you're also beginning to see actual solutions coming out of India. Is that
Yeah,
correct?
people are looking at the real problems now.
Real
And that's where
problems.
quantum advantage will also come from, right?
All
Like this
right.
protein folding problem from
Right,
IIT.
right. Fair enough. Uh, Vincent? Over to you.
Yeah, it's hard for me to describe specifically India because I do not have the numbers on the usage there. However, we see a very big increase in our usage as well, specifically from students, researchers. But not only that, I mean, we have very large customers all over the world, in Asia as well, who are not only looking on learning anymore, who are really developing their quantum teams because they want to create a quantum advantage. We have passed, I think, a bit the stage of playing around, and there's big investments in the research and algorithms. Well, they still understand that computers, like the physical computers, might be far away. There is a big increase, I feel, in teams that are serious, both in academia as well as in enterprise, that are really scaling up their efforts and preparing themselves for the moment that the logical quantum computer becomes available to take advantage of that directly. And we also see that in the students that are working with our platform who are creating more and more complex algorithms every single day.
Fair enough. I think that's a valid point. I have a very different question now, and open to it. Before we do that, Sujoy, your thoughts, and then we have a very interesting question which I'll open up to everyone. Yeah.
No, I mean, we also look around to see what people are doing with these computers, right? And it's quite incredible what people are already capable of doing. The algorithms that they're working out, the combination of classical and quantum, which is being thought about and implemented. So I think the fact that the software guys are already starting to use the machines in whatever form or format they exist, or starting to use the simulators to create all these algorithms, is very encouraging. So when the real machine comes out, that progress will be very rapid.
Great. So the interesting question now is that when we look at futuristic technologies from a computing perspective, there is also a little bit of focus that we see on problems that are it's still very, very limited. It's not that everybody is focusing on it, but you see a focus on neuromorphic computing. You'll also see a focus on biological computing. There is also very specific requirements for computing in edge scenarios, and we talked a little bit about that. So, any thoughts on how all of this is going to work along with quantum computing? Any early thoughts on that? And only anybody who wants to answer should answer. And I'm hoping I'll get at least one answer.
No. So I think this is what I mentioned sometime back as well, right? I mean, there will be tens or hundreds of different ways of computing, each of them good at doing something. And this is where the software is going to play a very important role. If you make those 100 methods of computing available to the end user, he's just going to get confused. So a point is going to come where you ping an Amazon cloud and you dump a program there, and it figures out uh, which computer/computers to ping to get the best answer, and you have the best answer. So I think that's where it's going to go. So everything will coexist. I don't think one will win over the other, at least in any near-term scenario.
Thank you for answering that. Any other thoughts on that? Otherwise, we move over to the audience questions.
I think the focus is completely on AI and quantum now.
Right.
Very little attention is going into, yes, there are pockets of people working on those, but right now I think it's, all the attention is on these two. The young people are moving here.
Right. Fair enough. So there is a question by Dhaval Yogesh Bhanushali. He says, how about Quantinuum? And Dhaval, if you are there, please unmute yourself, share your video, and just in case you want to explain that question. What is the context of how about Quantinuum? Are you there?
I'm sorry, I won't be able to switch on my video.
That's fine. Yeah.
We were talking about different modalities that could be the second best for each of Sujoy and Venkat. So I wanted to know their thoughts on Quantinuum. etc. How do they think them as their qubits, etc.? Because those are not the qubits that we can get access to or as learners.
Okay.
Yeah, actually, I've also not accessed them. I don't know. It's only the open systems that we know about. So unfortunately, I have no idea about them really.
Yeah, I think we don't want to guess. That's the best way to put it. I hope that they're building a really useful computer and all of us can use it shortly, but I have no idea.
They're using a quantum charge coupled device, so basically atom-based, ion-based technology. Atom and ion, yeah.
That's correct.
They're different,
Yeah, I mean, we kind of know what they do, but we don't know how well they do it or what they've achieved.
Yeah,
I
maybe.
think they have some open publications. They have. I think that's very impressive what they're doing.
Okay, great.
Yeah, I agree.
Yeah.
Yeah.
So, Dhaval, any other follow-up questions, or are we done on that question?
Just follow-up question was, say if one of these 15 technologies succeed, like Quantinuum is, we don't have access to Quantinuum's qubits, or we don't have access to Willow chip. So how do you predict the world to be? Will those chips be available to everyone? And if they will be, wouldn't we think that other technologies will catch up using that technology? I mean, quantum chemistry will be practical. You will be able to make materials that will work to create, say, a photonic quantum computer if superconducting is done. Thoughts on those two things?
So can I just answer a little bit about Quantinuum? Because Quantinuum, we have been in touch with Quantinuum. They are also interested in India, and they have been having conversations with us. So your first answer is easy. Question is easy to answer. Everybody who is developing a commercial quantum computer at a price will be available everywhere in the world, right? For programming, for using their computer, definitely, right? Whether it's on the cloud or a separate machine or so on and so forth. Except that there may be some restrictions, as we can see on the geopolitical side, there are restrictions coming up on the ingredients of the technology, right? So that is something which we cannot predict. We have to wait and watch and see what's happening. But in general, I think the answer is if somebody is willing to buy a quantum computer today in India, whatever they are selling, it will be made available.
I also don't really understand the question. As far as I'm aware, it is available through Azure. So you can use it now. You have to pay, of course, but it is available as far as I'm aware. Maybe my information is old, but according to the Azure website, you could use it right now.
Mm-hmm. Yeah, Microsoft and Quantinuum have a strong partnership, and yeah, so it should be available on Azure. Yeah.
Thanks,
I
Vincent.
think the
That's my
second.
try.
I think the second part of his question was very interesting. It comes down to the same question as whether AI bots will create AI bots, which will create other AI bots and destroy the world, right? So I don't know. It's a very interesting thought that a quantum computer will find materials which will build better quantum computers and so on. So yeah. Good luck. I mean, it would be good if that happens.
All right. Any other questions, Professor J.T. Andrews? Do you want to ask that question? You could unmute yourself. Yeah.
Yeah, good afternoon. So it was a nice interacting with all of you guys, especially almost all the three speakers as well as the moderator. Thank you for this meeting. So I like to iterate because many people are working on this area. Whether I say we're working on this area now, the quantum computer somewhat looks realistic. What is left for the academician or the new researchers who are thinking of taking up this quantum computing area or quantum technology or quantum materials area? So anybody can throw some light on it?
There is so much to do. There
Yeah.
is not enough manpower. There is so much to do. It doesn't matter what you do. Software, hardware, is the mountain of work is insane. So pick any topic and there's enough to do, whether it is about algorithms, increasing qubit fidelities, I don't think that there is anywhere where there's nothing to do.
Yeah, control systems on the hardware
Everything.
side and error correction and memory storage. How do you store quantum qubits better? I mean, the scope is like if you look at every aspect of a computer or a communication channel, there is I would say that there is 5% done and 95%. Don't hold me accountable for those numbers, but just to give you the magnitude, I feel that there is 95% to be done. So any area can be picked up to be made better, any sub area within.
Yeah, but sir, all these area people are already working with classical system. So the other you can say GPU or CPU, they are already using it. Even some places supercomputers being also used. So the same thing, just directly if somebody wants to go to the area of quantum computing, for example, error correction or simulation, or if you are finding a polymer material. So the one easy route, I feel it is to cascade. Of course, we are also learning. There are lots of other people in our group also learning. We are trying to find this could be one group to which we can go into.
So
But
I
what
think,
else is that?
yeah.
Yeah, yeah, please.
I was just saying that's a slightly different question, and we'll be happy to help you. Maybe we can connect offline. If you're
Sure.
working on supercomputers, then looking at HPC architectures which interface with quantum QPUs is actually a good way to look at it, or finding adjacencies is good. Like, so for example, if the strength is AI, then there are a lot of people who are doing quantum AI and looking at how that could give better solutions. So that's my answer in general, but I think if there is more specific answers required, then a detailed discussion can happen with the small, I mean,
We'll connect with you.
Anuj Mehlotra, you want to go ahead and ask your question? Modular scalability?
No, I will. Hi, Rina. This is Anuj. So I have an observation. I think I was listening carefully to Venkat and Sujoy and Vincent. So I think they were all mentioning about the scalability, but I think the basic thing which is actually there for scalability is modularity. Okay, so without modularity, you can't have scalability. And for like if you have scalability, you will have quantum advantage. But and both of like they were mentioning about like I think Sujoy mentioned about the distributed nature of actually connecting the some of the edge devices. But that is the way forward. So we keep on arguing about the modality which will win. Okay, but the thing is like any such modality which has like quantum networks and distributed computing, entanglement based computing in their roadmap, they are the ones which will be actually succeeding, as per me. And there are limitations also, which Venkat also mentioned on the like error correction. And just for the clarity of the audience, the error correction limitation actually requires that all the neighboring like there should be like end-to-end more connectivity across the qubits,
So,
and
Anuj,
that
what's
is
your
something
question?
which cannot be achieved.
Uh, so,
No, it is an observation. I'm just telling. I'm. Can I go on or should I pause?
I mean, depends. Question is usually short. Observations are usually very
No, my
long.
question is no, no, my question is that because we keep on mentioning about a lot of actually like scalability, we talk about the error correction, but there is all these things are interconnected. Okay, and the basic thing is actually distributed computing should be there in the and the roadmap. If I talk about IBM roadmap, also it is doesn't mention about the distributed computing because the L coupler, C coupler, M coupler, they are not actually networking. They are simply the interconnects across the chips. So when we can expect from India or from like IBM, like Sujoy, actually focusing on this particular distributed computing, and mainly if I talk about like I'm talking on the level
So
of the
I will take
transducers.
one. So it gets confusing. So I'm taking one question from you. Let them answer that, and then if there's another one, we'll see. The first question you had is about this modular scalability, and also about this distributed computing, and if anything is there on the roadmap, and if you have any comments on that, Venkat and Sujoy.
Yeah, so I think that's what when we talk about quantum supercomputing, we're actually talking about that only, that, you have multiple processors connected and you are now building a 1 lakh qubit supercomputer, quantum supercomputer, basically, right? And that's what the 2033 target is, 1 lakh qubits all connected across each other. But what I really liked about Anuj's question is the commercial killer apps. Okay, that's the key, because all this work, whatever we are doing, all this research for error correction, this one, that one, it is for what? It is to solve some realistic problem, right? And I think this is where we also go back to Dr. JT Andrews' question. And if you look at the history, what did FC Kohli do before he started TCS? He went and sat in IIT Kanpur. Oh, we have this computer. What do we do with this? Which problem can we solve with this? That's what he figured out for 6, 7 years before he started TCS, right? And I think that's what we need to do. I mean, like Anuj said, of course, error problems are there, error correction is limited, scalability is not there. But using the 100 plus qubits now, we have said 2 years we want to reach quantum advantage. The question is, are we going to reach it out of India? Are we going to be the FC Kohlis who will sit and ponder, which is that problem we can solve using this quantum computer, which we can't solve using the classical? I think that's the very interesting question, that with the current computers, what is it that we can achieve? Because people are already, like, Vincent mentioned, a lot of good results have begun coming up. And in the next 2 years, it's going to happen. And it better be out of India, given all the talent which we have. I think that's really what the focus should be. And I like that part of Anuj's question where he's asking about the commercial killer apps. And that's what we need to focus on.
Sure. So I hope, Anuj, your question is answered, the question that was asked. Anything else you have?
So I'll add to that. So the killer app will be the ones which can actually explore this distributed quantum computing. Okay. So
Okay.
any applications, because we talk about Grover's algorithm as of now are not feasible on the current NISQ computing, but that will be feasible with the like distributed quantum computing. So supercomputing roadmap which we have seen, and I think Dhaval also pointed out that particular point in his chat, that so far IBM has not disclosed that how they will be connecting that 2033, that goal is there to have a supercomputing of 100,000 actually qubit, but how they will interconnecting, that is still the thing which we see on the portal is L coupler, C coupler, M couplers, but there is no mentioning of the quantum networks. How, what is like, are they all planning to use transducers? Are they relying on the quantum repeaters? Something of that sort. There is no direction given on this particular topic.
So may I step in, and I cannot comment on the IBM front, but one thing which I can share with you is that not only computing, there is a lot of work that still needs to be done on the communication side. So while we easily talk about quantum repeaters and quantum gateways and stuff like that, quantum memories and all, they're all in very early stages, by the way. So as the communication stack evolves, the hardware capability on the communication side evolves in quantum, I think the roadmap will become clearer for how computing and networks are going to integrate with each other to create these scenarios. That is a general answer from my side. I mean,
So,
I'm
so,
because
so
I'm
I
looking
think
at.
I think just to clarify, quantum repeaters, quantum memory won't be required for the QPU clustering. Okay, if you have to cluster the QPUs, you don't require that. What you require is controllers and transducers, and those are the areas where I think there might be few pockets I think who are working, but that is not largely discussed in many forums, and that is the way forward how we will actually achieve the distributed quantum computing.
Yeah, sure. There may be new kinds of interconnects that might be discovered and which may be more suitable as well. I think we have to wait and watch on that, right? And companies only tend to disclose what they want to disclose at specific points, which is okay in a competitive environment. I think that they can. I mean, share. But over to you, Venkat, if you want to answer anything more specific.
No, I think the point I'm saying is let's not wait 10 years. Let's use what we have today, and people are going to, whether we reach it or somebody else reaches it, that's the question. And it better be us. That's the answer.
Okay, great. Um, any other questions? Anybody else wants to have a question, ask a question? Please raise your hand in the system or just unmute yourself and ask the question. Yes, Shantanu, go ahead, please. Shantanu, you can go ahead. You have to unmute yourself.
Am I audible now?
Yes, you are.
Yes. Hi, sorry, apologies. I'm Shantanu from QETCI. I had a question for all the panelists. What are some of the challenges your company faces and you guys face as well when interacting in the ecosystem, given how you're situated in the tech stack? And also, what are some of the challenges you face when communicating your work as a business study as well?
So one big problem, at least I see, is people have very varied kind of expectations from quantum computers. Some think it's a new kind of supercomputer. It will solve all the problems. But I think the focus needs to sort of shift to, quantum computers are good for certain tasks. I have in my company, I have these workflows, and these are my use cases and tasks. Which of them is very good for trying on a quantum computer? I think that's where getting people on that journey of like, for example, you're a bank. So in a bank, you do many transactions. So transaction processing, you don't want to mess with it. You're probably doing on a mainframe, you're doing it on some Linux cluster or whatever. But if you want to do fraud detection on it, today the techniques fail. They're not real time, they take a lot of time, they're not accurate. So is that a problem for the quantum computer to try and solve? Should I be moving that workload to, or parts of that workload? I think those questions, when industry starts asking, those are the right questions, because yes, quantum computers can't do everything today. They have a lot of limitations. Error is there, and coherence time is low, everything is there. But are there parts of my workflow which I can deploy on the quantum? I think many industries around the world have begun asking those questions, but probably not enough of them. And that will happen eventually. Once you start seeing these use cases getting deployed and success coming, more and more will jump in. But the question really is, who are those pioneering industries who want to take the lead and get that business advantage? I think that's the question, really.
I think what I hear you say is that the end user needs to be more trained, right? And made more
Yes.
aware, and that would really solve the problem of adoption. Any thoughts from you, Vincent and Sujoy? Any other business challenges or any comments?
I think overall, it is a market that is flooded with different views on topics, and very basic definitions aren't already, like, nobody understands things. So it's a very quickly emerging market, and that makes it difficult for, I think, for businesses to see, okay, where are you positioned? What is the part that your company tackles, and where does it end? Where does it start? These type of things. Of course, you have companies at IBM that can have the whole stack, but then yeah, I feel it's pretty difficult to really show what is it that you do, because it's such an immature market yet, and where does your specific company add value? It's not easy.
Mm-hmm. So value needs to be understood more appropriately. And I'm like kind of thinking how QETCI can help in that. Like, so
Yeah,
that's interesting
and
because
when you brought up this point, Reena, I really, a bulb lighted in my brain saying that we are seeing students adopt it. We are seeing the early, the low, those who are at the in companies coding, but we are not seeing the CEOs and the CXOs. I mean, they know, they are trying to understand what is quantum, but I think they need that sort of a crash course on what is quantum, how do you get it done, that roadmap, and maybe that's where QATCI comes
I
in.
think Shantanu got his answer now. Shantanu is focusing a lot on education, so I think he got his answer now as to. Yes, Sujay, please go ahead. You are on mute though. Unmute yourself. Yeah.
Okay, super. I think yeah, Venkat kind of made the point for me. I think people out there, the people in industry, are thinking of quantum as incidental reading. The 1 hour which my coach has told me to spend before bedtime, I'll just read about quantum, but it's not really related to my core work. And if you can help change that by going out there and telling people that a narrative has been spun in the world by people. I don't want to name any people who that quantum computing, just ignore it. It's 20 years in the future. Don't worry about it. You will be retired by that time. Focus on other stuff, right? So I think we need to come up with that narrative that it's real. Some things can be done right away. We need to start focusing on it, get value out of it. I think that would be a great thing if that communication can go out.
Sure, I think that's a great point. And I think all of you echoed the point in different ways, so those are valuable inputs. Uh, Mr. Colonel Eknath, I think
Yes,
that's you,
yes.
right? Please go ahead.
Good
Yeah.
afternoon. Yes. So I would just like to ask the panelists, what is their view on the role being played by the simulators today, quantum simulators, and as we progress, like they are very playing a very important role for initiating students and researchers, people who don't have access to the platforms, the costly platform. So, what would be the role which will be continued to be played, and how will it progress in the years to come?
So
So
from the
I
software
think
side, sorry. So from the software side, simulators are, at the moment, at least for large algorithms, extremely important. I mean, we cannot do anything without them. And not only to test hardware on qubits, but also understand the effects of errors in larger systems and how we do that. So for us, we use simulators every single day, and especially because the algorithms that our customers mostly develop are so big that in the near future it's simply impossible. And we also see a lot of interesting development in simulators themselves, novel ways to get more performance out of simulators. So I'm not sure if simulators will ever sort of have an advantage over classical ways of computing. But I think for the foreseeing future, simulators will be extremely important to help advance implementations of algorithms and actually advance our understanding of how algorithms will be executed on large scale and future computers. So for us, these are extremely important.
Yeah, so I'll add that simulators are extremely important, as Vincent said, for mostly for education purposes. But until we are using simulators, we know we have not done the job, because the real thing is the quantum computer. If you are not able to use the quantum computer eventually, then you are not getting any advantage out of it. Okay, it's just a as Sujoy mentioned, it is something you do on the side. So, and what we are also seeing today is that mostly it is the physicists who are in quantum computing. And that needs to shift to end users, the computer scientists and the applications people. Until they come in, we know that this is still a lab device. It's a thing that sits in a lab, which is not useful in the real world. People are using it to learn. And I think the real test happens when, and that's the reason why IBM threw away all the under 100 qubits, right? Because until you are using simulators, you're not, you can as well go and use your laptop, right? Why even use the quantum computer? The real power of the quantum computer, the quadratic speedups, the exponential speedups, are only going to happen when you really solve problems on the quantum computer.
Those are two.
I do not really completely agree with you there, because we still need to develop these large scale algorithms. It is more than just playing around. I think simulators have a higher value than just that. I mean, they even though they are relatively small scale, we need to validate that large algorithms like HHL, Shor, they work even before, and test different implementations. So I think even in a world where you have quantum computers, still simulators for testing, for development will still have a place where, and not only quantum computers will be needed.
Yeah, so I see a space for, I mean, when I hear both of you speak, I see it like a continuum. Like, I see different uses for both. Like, on the simulators, you continue to work on the futuristic algorithms. You develop a new algorithm. It is a scaled up algorithm. You cannot obviously test it on the computer. And if you need to deploy something right now with existing algorithms that have already been tested, then you go for the quantum computer. So I think in some senses, both what Venkat is saying and what Vincent, you are saying, I think both are applicable. I think the context is different, and I would not, I would say both are important because it's an evolving area and we still have a lot that needs to happen in this space. And the scope and the usage and where it is being used, by whom it is being used, that may be different as we move forward, right? All right. Any other questions? I think we have time for one last question. Very quick one because we have only 1 minute left.
I will add to what actually Venkat was saying. Okay, awareness is fine for the leadership, but you have to work not only for the like on the awareness part, but you have to work with them for the business plan, which will have the business value. So you can't leave with the leadership with just with the awareness. You have to work, and there can be a in plan that they don't want to go with the quantum. That is also be part of their business vision. So I would say awareness is fine, but for the leadership, we have to work on the business plan also.
Sure, sure. I see some more questions coming in. I don't know if everybody's willing to wait for a couple of more minutes. Should I take another question? Panelists? Okay, one final question. Vandana, why don't you ask your question?
Am I audible, sir?
Yes, you are.
Yeah. So, my name is Vandana Chaturvedi. So, I want to know, as per speaker's personal perspective, your personal observation, that how you see the difference between running a good potential program over a good simulator versus a real quantum simulator. How you see the difference? What you have feel that this is the difference or something?
So when you run the same program, can I qualify your question and please tell me if it's
Yeah,
right?
please.
If you run the same program on a simulator versus on an actual machine, you want to know if there is a difference that somebody would see, right?
Yeah.
Okay.
Yeah. So the simulator is up
Yeah.
to 30 qubits, right? So anything beyond that, you can't really simulate, right? Maybe you are breaking up your algorithm to run on 30 here, 30 there. Maybe that's what you will do. Also, you don't get that because we have shown in simulations, right, that beyond about 70, 80 qubits, you cannot, achieve the same results using any simulator if you wanted to also.
Yeah, actually, in the result perspective, I want to know that I am going to change the result that actually. Yeah, okay. Thank you for your answer.
Okay, thank you. I think we had a really great discussion today, and I'm sure there is scope for more, but we have more sessions lined up to clarify more things. And as usual, thank you to the audience for being active and asking questions. But a very big thank you to all our panelists. Thank you for taking the time and being here and sharing your knowledge and opinions. It's very useful for the community. So please continue to participate, and thank you, everyone. With this, we will wrap this up. Bye-bye.
Thank you so much. Thank
Thank
you.
you.
Thank you. Bye.
Bye.
Bye bye.